So if you go to the course website here, go under test exam, and there will be the lab test preparation. Okay? The starter code will be pretty much what you will be given during the lab test. So there might be one or two, I think decided yet. There might be some contract that I will comment out for you to complete. I'll try to make them minimum, because the main task is really to implement undo review pattern for the which you have to read the chapter in order to do it. Okay?
So no EPF?
Okay, so let's go to the second one.
So what about the ETF? Do you have it known?
The ETF?
Yeah.
Okay, that's a good question. So I decided to give you guys a simpler task. So you only have to use the ETF for the projects, not for the lab test. I also found that maybe it took way too long to compile the ETF in the lab test. That would be a waste of your time, right? So now you guys have no excuse for the lab test, right? You might still have some, but hopefully not less. So you have to use the ETF for the project, that's for sure. Okay, so now the second pattern I'm going to talk about is somehow also related to the composite pattern. So make sure you actually study the two patterns, one after one. And for the project, which I will demonstrate maybe after the second break, the project, I'll talk about it actually. Let's finish the physical patterns first. I wonder, when you study your Java course, did you actually talk about the physical patterns? Okay. So now So now this is the problem we're having now. So let's say we have, so this is almost like composite pattern. Let me just elaborate that a little bit. So this is like an example I talked before the break, which is about how to represent the small language for expression. In this case, we have some expression here, so that's a generic concept there. And we also have constant, which is more like a basic expression. And here we have addition here, which is more like a composite expression, right? How would you draw the diagram more closer to what we discussed before the workshop? So here you have expression here at the top. Okay, so here you have the basic expression here. So for example, we might say basic here. Okay, and then so here basic, one possible basic expression would be simply a constant, let's say. Of course, for the constant, you might divide that further to say it might either be a real number constant, it might be an integer constant, it might be a Boolean constant. But let's not go with that complexity for now. So that's one category. The other category is the composite expression. Composite expression here. So I can say composite expression here, just to make the name more informative. Okay, so here you can say basic expression. Okay, now remember the key about the composite pattern is we are trying to differentiate between basic and composite expressions in this case. So what we have to do is to make sure this kind of expression here can have a list of expressions. Okay? So here you might call that children with a generic name, or you might simply say let's say expression list. It would simply be, let's say, a list of dot. In this case, dot means expression. Okay? For the composite expression here, we now just have addition. Now somehow you can relate this to how would you represent the syntax of iPhone using the composite pattern. That would be a very interesting exercise to do. So you just think about, even for just the composite part, let's say for the operator, you might have binary operator, you might have unitary operator. So for example, you might have plus, you have minus, you have multiply, multiply and divide, so each one of them should go to a separate class. And also, you have the logical operators, you have the AND for conjunction, you have OR, you have implies, and also you have unary operator, you have not. So that means when you're trying to define the composite expression here for either language, let's say, or even for Java, what you have to do is more advanced. Then you actually create some intermediate abstraction to say, for the composite expression here, I might have either unary expression or I might have binary expression. So now under unary expression, I will have the negation here. And under binary expression, I will have these here. Okay, let me just write it down to make it more concrete here. So under composite expression here, so you might have, let's say, binary, which means it has two operands, right? So please make sure you really know the difference between operation, operator, operand, right? The operator would be something like plus, okay? Operand can be 1 or 2 or 3, something that you can apply the plus into. Okay, operation would be where you combine an operand and operator together, let's say 1 plus 2. Okay, so these are just terminologies for you to keep in mind. You actually write into these for your project, so please make sure you understand them. So now for the binary operation here, so here we might have, I just give you some examples. So for example, addition there should be a binary operation here, so I would say addition here. And now we might also have unary operation here. So for the unary, so we might have let's say negation, logical negation, I mean. Okay? So now, up to now, for this particular example, there will be one small improvement you can make in terms of how you define the expression list over here. Okay? Just for this particular example. So let me just sketch that for you. You can try to practice that yourself, most likely in your projects. So now, before we simply say each composite has simply a list of expressions. But this might be a little too general. But that means now for the binary operator, because that's actually composite, so you might have more than 2 operands. It's actually allowed. Because it's simply a list, it doesn't say anything about the how long the list should be. There are 2 ways to restrict this. Either you put a class invariant here, okay? In the, let's say for the binary class, so you would say invariant, you can say the expression list dot count equals 2. Okay, and for the unary operation, you would do similar. You would just say expression list dot count equals 1. That's one way to constrain. Okay. Now the second way to constrain that is simply we try to get rid of, let's say, get rid of this guy here. Okay, somehow we want to customize that for each individual class. Okay, let me do that. Let's say we get rid of that. So once I get rid of that, so now for the binary, I know that it should have only 2 child expressions, right? So here I can simply just do left and right. So it's actually easier for you to actually get access to the 2 sub-expressions rather than say child number 1 and child number 2. So here I would say left and right should be simply expression. Okay? And here for unary, I can simply have a single expression here of type expression. And the advantage of doing this, like a second solution is, I don't actually have to specify this invariance. And actually don't need this arrow here. I'm simply just saying, now for this binary expression here, of course, now the client supply goes this way. Right? It looks slightly more complicated, but it depends on which one you prefer. There's no really no better one. Okay, so please make sure you see the 2 solutions. Okay, let me just write it down for you, so please do think about that. So now, solution 1. So you can put 1 plus invariance in binary operation there. So you can say something like the children count equals 2. That's solution number 1. So now solution 2. First of all, you have to eliminate the client supply link from composite to expression. That's step number 1. So which means you're trying to get rid of this link here from composite to expression. That's solution number 1. Solution number 2. And then after you have done that, so now the binary operation, you would say left and 1. It's simply a binary tree rather than a general tree. Oh, this is left and right in the expression. And now, in unary operation here, you simply say expression to the single attributes. Okay, you can see the 2 different solutions. You can choose either one you like.
Hey.
All right. Should have only found this solution now. Yes.
Is it children count equals 2?
Equals 2, yes. Yes. Okay, so make sure you know about these 2 solutions. And yep. Okay, so now let's say we have this class hierarchy here to represent this simple expression language here. So now let's say we're trying to support different operations for language. You know, let's say you're given a small programming language to process. Let's say we want to evaluate, for example, let's say if I give to you, let's say 1 plus 2, so of course you give me 3. Or if I give you true implies false, you give me false. Things like that, right? To evaluate, or you may want to print in different order. So you might print in an infix order, you might print in a postfix order, just different operations. So now, this is one possible design. So this is to say, let's say we start with simply the language structure without any operation supported. So now, let's say, now we do want to support the evaluates, so we define the evaluates on the top as deferred. Okay? Let me just clean this board, and then I'll show you. One more detail. So here you can see that this part is about the operation here, and this part is about the structures. So the only thing, you got one last thing to do, only one feature you have to say is, I'll explain how this works, but somehow you want to say, now if I have this particular expression, how can I somehow get some link to the visitor? There's only one link you have to draw. So you would say accept visitor. So that means we are sort of drawing a link here. So that means now is rather than having inheritance relationship for the operations, we actually have client supply. This is to say, whenever we want to evaluate or to do apply different operations to the language, to the expression language, we can actually simply use the facility provided from here, rather than those that's inherited. Okay? And so we have a look. how this is going to be runtime. Okay, first of all, let's see how this works from the client's point of view. So now let's say, so now I'm talking about expression here being the client and the visitor being the supplier. So let's see how this cascade works. So let's say we have different expression here. We have addition here. We have constant. We have constant number 1, constant number 2. And we have 2 different visitors here. So we have the evaluator and we have the printer. So now this is actually related to how we do the composite pattern from the previous, before the break. So this one should be not so surprising here. So this is just how you do IFO to say, now I want to initialize a constant from the expression, which is possible. So now I'm creating a constant 1, constant 2, and now addition is actually a composite expression. I'm now adding constant C1 and C2 as is left and right. And then, now, this is really the key, how you actually use the visitor pattern here. So now I'm saying, now this particular expression here, whose current shape is actually an addition. I'm going to do some visit there. What kind of visit I'm going to do? It depends on what's the dynamic type for this particular visitor. Because when you have a look at here, this type here is very general. It's actually simply a visitor. I didn't say anything about what kind of visitor it is. It can be evaluator, it can be a printer, it can be a type checker, for example. It can be anything. So here, I simply say, I pass this evaluator as the argument, and dynamic binding is going to do the trick. Okay? That's how you use it. And typically, in the visitor class, you should have a value attributes. You'll be very useful for your project. So for each of the visitor that most likely you will define, you should have some kind of attributes for you to retrieve the results of visiting the expression language. In this case, we're trying to say, let me draw some object diagram for you. So here we have addition here. Let me just make it simple. I'm thinking left and right here. And then we have 1, and we have 2. Okay? And that's simply add. Okay? Okay, I'll give you just maybe, you know what? I think it might be easier. Let me give you 1 minute. Think about how you think this will actually work. So now maybe just write on this line here to say eval, here, this line here. When I say add visit eval, what's going to happen? According to this diagram here, think about that. So what we know is, this accept, let me write this line here. So when you say add